Hello, everyone. My name is Sri Abhyankar, and in this paper, we are going to be presenting a new dynamic simulation application that has been implemented in the GridPACK framework. This work is done jointly with my colleagues at PNNL and Clemson University. So the objective of this paper is to introduce a new dynamic simulation application. This new dynamic simulation application uses implicit integration algorithms as compared to the existing explicit alternating algorithms that are used in the industry. And this new dynamic simulation application has been added to the GridPACK package. We'll discuss the features of this new dynamic simulation application in detail in this paper, and I'll be presenting it in brief in this presentation. Finally, we will go over some of the accuracy and the parallel performance for simulation of large-scale networks using this new dynamic simulation application. So this new dynamic simulation application that's been added in GridPACK, the differentiating feature is that it uses implicit integration algorithms. Implicit integration algorithms are much more stable than its counterpart explicit algorithms because they have better stability guarantees. And there are a variety of these implicit algorithms that are of different orders. We have interfaced the implicit algorithms from the PETSc libraries, and that range from having just a simple first order backward Euler or a second order trapezoidal, Runge-Kutta, Rosenbrock, and all the different integration algorithms, implicit integration algorithms that are available via PETSc. The new dynamic simulation application is fully parallel. So we do a domain decomposition approach where we partition the network into subnetworks, and each subnetwork is the responsibility of or is assigned to a different process or rank. And there is exchange of information at the network borders. A main feature of this new dynamic simulation application is that it can adapt the step size. So as the dynamics change, the step size is adapted to be much more efficient. The calculation shown over here shows the calculation of a new step size, delta T new, based on the previous step and an evaluation of what is called as the local truncation error. The last feature of this new dynamic simulation application is that it can handle the discontinuities that exist in dynamics from events such as faults or line trippings or some controller hitting its limit and so on. And we provide support in a much more structured way by calculating when the exact event 0 or the discontinuity happens. This provides a much more stable way of handling the discontinuities as opposed to the existing way of not finding the event 0. We ran this new dynamics simulation application on as large as a 12,000 bus system, which consisted of thousands of generators, loads, and so on. And we compared the performance of this new implicit variable step algorithm with the existing approach in GridPACK, which is the fixed step alternating explicit method. The table on the left shows the performance of these two algorithms ranging from 1 core all the way up to 32 cores. The numbers given in columns 2 and 3 are the execution time for the two algorithms. As you can see, the implicit integration algorithm takes less time than its counterpart alternating explicit. The figure on the right shows the accuracy comparison. It compares the frequency of a certain generator using the two approaches. And as you can see, the implicit algorithm shows qualitatively the same trajectory as its alternating explicit part. So we also have a good accuracy for this new dynamic simulation application. So to summarize, we've added a new dynamic simulation application in GridPACK. It has implicit integration, it can do variable time stepping, and it is fully parallel. As shown in the tables in the last slide, it shows good speed up for large scale systems. And variable time stepping is a desirable feature when one wants to do long or extended time period dynamic simulation, such as those would be required with large penetration of renewable energy resources where the system inertia is low.